This is the last episode of chapter 9, which is also one of the most important content of chapter 9. The topic of this episode is Le Chatelier's principle. What is it? What is it used for? Well, let's answer the second question first. What is it used for? We have been talking about equilibrium for some time. We know given a set of conditions, a chemical reaction will reach an equilibrium state eventually. Well, if for a system under equilibrium, if some of the conditions changes, then the system will no longer be in the equilibrium. It is going to readjust itself. Given enough time, a new equilibrium will be built under the new condition. Well, under the new equilibrium, the amount of the reactants and the products will be different from the previous equilibrium. The Le Chatelier's principle helps you to decide, under the new equilibrium, how the amount of the reactants or products will change compared to the original equilibrium. In other words, when some of the conditions changes for an equilibrium, how the system will readjust itself so that to reach a new equilibrium. Well, this is how it states. If a stress is applied to an equilibrium, a stress means a disturbance, a change. If a stress is applied to an equilibrium, the system will readjust itself in the direction that best reduces the stress imposed on the system. Well, I'm not sure if the statement is easy to understand or not, but let me put it in a simple way. If I am in the equilibrium right now, I am in a very stable state. If someone does something to me, that means a stress. If someone applies a stress to me, I'm going to respond. I'm going to respond in such a way that I will try my best to reduce the impact of what you did to me. That's the Le Chatelier's principle. If some conditions is disturbed for an equilibrium, the equilibrium is going to try to respond in such a way that it will reduce the impact of the change applied to the system. Hope that helps. If it doesn't, don't worry, we will go through this again and again in the later slides. So regardless, we know once a change is applied to an equilibrium, the equilibrium will readjust and a new equilibrium will be built. Now, under the new equilibrium, if there's more products produced than before, we say the equilibrium shifted to the right. Reactants in equilibrium with products. If something changed and as a result more products are formed, we say the equilibrium shifted to the right. Okay, the stress applied caused the equilibrium shifted to the right. If as a result of the disturbance, more reactants are formed, okay, under the new equilibrium, there's more reactants than before. Then we say the equilibrium shifted to the left. Now let's look at some of the stresses or changes that we will encounter in this class. Number one, concentration changes. When a reactant and products in the equilibrium, at this moment, if you add some of the substances, be it a reactant or a product, in other words, if you change the concentration of some of the substances, the system will shift away from the added component. Makes sense. I am in the equilibrium. If you add something to me, I am going to try to move away so that I will reduce the amount you add to me. For example, if you are you routinely you go to work, you earn a certain amount of money each week, and given time, you know how much you earn each week, how much you will spend each week. You are in the equilibrium in your life for that period of time. Well, suddenly, at 1 week, your boss comes to me and tells you, hey, blah, 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 I want you to work more hours this week. Well, you worked more hours. 2 weeks later, you get your paycheck. You get a lot more earnings than before. The original equilibrium is disturbed. Now the money earned is way more than what you usually do. What very likely to happen? You may take the money, happily spend some of them. Does that make sense to you? You may spend more than before. That's what it is. If you add something to an equilibrium, the system is going to shift away from the added component, which means it's going to consume some of the added product. If a component is removed from an equilibrated system, the system will shift towards that direction to produce more. It's like 1 week, you spend a lot more than you expected. Then what do you do next week? You work more hours to earn more money. That's what it is. So here's the example. The reaction is nitrogen reacted with hydrogen in the equilibrium with ammonia right here. Right now, the system is in the equilibrium. The concentration of nitrogen, hydrogen, and ammonia is at 5, 7, and 5, let's say molarity or partial pressure. Now you add more hydrogen to it. You add 3 molarity more hydrogen to the system. You applied a stress to the system. The equilibrium is broken. Now, how will the system readjust itself? How will the system respond? You added hydrogen. I am going to try to consume the hydrogen. To consume added hydrogen, the system will react to the right. You react the hydrogen with the nitrogen. As a result, more ammonia will be produced. Less ammonia will be left than before. Here we go. Eventually, more ammonia is produced. The amount of nitrogen is less than before. The amount of hydrogen, of course, is more than before because you added hydrogen. However, it is less than the original amount plus the amount you added. Why? Because the amount you added, some of them is consumed by shifting the reaction to the right. Did I make that clear? It's like 1 week you earn a lot more money than before. Likely next week you will spend the amount the extra amount, but you are not going to spend all of them. Very likely you're going to save some and spend some of them. All right, so again, concentration change. If you add a component to the system will shift away from the added component. If a component is removed, the system will shift towards that component. Temperature. KEQ will change depending on the temperature. We talked about this. Let's use again endothermic reaction as an example. We went over this in the last episode, but here with Le Chatelier's principle, let's talk about it again. So we have an endothermic process, reactants plus energy. Energy is considered at the reactant side for endothermic reaction. Now the system is in the equilibrium with the products. If you raise the temperature, if you increase the temperature, again, how do you increase temperature? You heat it up. You're applying heat. you're adding energy to it. When you add energy, you add a component like we just learned on the last slide. If you add a component, the equilibrium will shift away from the added component. You raise the temperature, you added energy, it's going to shift to the right. As a result, more product will be produced. Less reactants will be left than before. So for an endothermic reaction, raising temperature will shift equilibrium to the right. If you understand that, then for an endothermic process, where energy is considered a product, raising the temperature will shift the equilibrium to the left. Well, here is an example in reality. Okay, what we learned on the last slide can be used to predict whether a reaction is endothermic or exothermic. This is the equilibrium between two substances. One substance is blue, one substance is pink, and they are in the equilibrium. I put the blue substance, I used the color blue to represent the blue substance, used color pink to represent the pink substance. Okay, if this reaction goes to the right, the system will become more pink. If this reaction goes to the left, the system will become more blue. All right, here's the experiment. Under the room temperature, you fill it up with the blue substance. You place this one into an ice bath. When you put something into an ice bath, temperature is going to get lower. You are actually taking energy away from the system. When you take energy away, the system is going to shift towards the direction that produces more energy. That's Le Chatelier's principle. You're taking something away, I'm going to produce more of that. If you add something to us, we're going to consume the added stuff. Right now, you place the jar into the ice bath, you are taking energy away. We know the system will shift towards the direction that will produce energy. Does that make sense to you? Well, clearly you place it into ice bath, it becomes pink. That tells you to that direction, energy will be produced. That's why when you take energy away, that's why when you take energy away, the system will shift towards that direction. For this process, we know energy is on the product side of the reaction. Therefore, this reaction is exothermic. Questions like this may very well appear in the quiz or exam. Pressure. Well, pressure will only affect the equilibrium if gases are involved in the system. If all the reactant and the products in the reaction are either solid or liquids or in the solution, pressure has no impact to the equilibrium. If gas is involved, here is what we need to know. A, the system will shift away from added gases component. Well, the same as what we learned for the adding or removing a substance. If the component is removed, the opposite occurs. Number two, adding inert gas, adding something that is not related to the reaction. Doesn't have to be an inert gas. Anything that has nothing to do with the reaction, addition of something that has nothing to do with the reaction will not affect the equilibrium. Decreasing the volume, okay, if you decrease the volume of the reaction container, the equilibrium will shift towards the side with fewer moles of gas. Why? Well, let's talk about this. Let's say I I am standing in a cylinder, okay, in the vertical cylinder. I'm standing inside. On top of my head, we place a cap, a metal cap on it. Well, a metal cap on top of me, if no one pushes, I'm okay. I'm stable. I'm in the equilibrium in the cylinder right now. What if now someone start to apply pressure on top of the cap? Someone trying to reduce the volume. Well, reduce the volume, increasing pressure, similar. Okay, someone try to push the cap, try to reduce the volume of the cylinder. Well, I'm in trouble. I know that because it hurts on the top of my head. It hurt. I am going to respond. How do I respond? You push the cap down. I'm going to try to shrink myself so that I take lesser volume. When I take lesser volume, it doesn't hurt too much when you push it down. Does that make sense to you? That's how an equilibrium will readjust itself when pressure is applied or when volume is reduced. They will try to take lesser volume than before. How to take lesser volume? Lesser amount of gas, lesser moles of gases will take lesser volume. Does that make sense? That's Le Chatelier's principle. When you apply some change to me, I am going to readjust myself so that I will reduce the impact of what you did to me. All right, let's look at an example. So we have learned a few changes to an equilibrium that will affect the equilibrium position. We applied, or we learned addition and removal of some components. We learned temperature change. We learned pressure and volume change. So let's use this example to go through all of this. We have an equilibrium on the left. We have 1 mole of methane gas react with 2 moles of hydrogen sulfide gas to produce carbon disulfide gas and 4 moles of hydrogen gas. All gases in the equilibrium. This whole reaction is endothermic because heat energy is on the reactant side, is endothermic. How will the gas phase equilibrium be affected by each of the following? Let's look at what we have here. The removal or addition of H2S. Wow, this is easy. If you remove H2S, the equilibrium is going to shift to the left to produce more. That's Le Chatelier's principle. I'm going to readjust myself so that I'm going to reduce the impact of what you did to me. So you remove a component, the equilibrium shifts towards to that component. Addition, if you add H2S, then it's going to shift to the right. Does that make sense to you? All right, you can try to use other substances, try to do removal or addition of any other substances and predict if the equilibrium is going to shift to the left or to the right. Again, to clarify, the removal of H2S will cause the equilibrium shift to the left to produce more H2S. Next, increase in temperature. Increased temperature means adding more energy. This reaction is endothermic. Energy is on the left. Increased temperature, you are adding energy to the system. The system is going to shift to the right. Does that make sense to you? If the question is asking you decrease in temperature, then the answer will be shift to the left. A decrease in the volume of the container or an increase in pressure, decrease in volume, increase in pressure, similar, okay? Decrease in volume, we just learned decrease in volume will shift the equilibrium towards the side with fewer moles of gases. All right, on the left, we have 1 plus 2, 3 moles of gases. On the right, we have 1 and 4. 1 plus 4, we have 5 moles of gases. To go from left to right, 3 moles becomes 5 moles. To go from right to the left, 5 moles becomes 3 moles. So if you decrease the volume or increase the pressure, the system is going to shift towards the direction that has fewer moles of gases. So decrease in volume, increase in pressure in this case will shift the equilibrium to the left towards the 3 moles direction. Well, if the question is asking for increase in volume or decrease in pressure, the system will shift to the right. Hope this practice helps. We're not done yet. We're almost done. So in the questions about Le Chatelier's principles will be asked repeatedly. Well, regardless how it is asked, it's going to be about concentration changes, addition, removal of something, temperature changes on endothermic, exothermic processes, pressure changes on gases. Okay, but one last change. Another change that can be applied to a reaction system is the addition of catalysts. A catalyst does not alter the position of an equilibrium. What it does is that it can make the equilibrium established faster. So if there is a reaction system that is in the equilibrium, and then you add a catalyst to it, none of the concentrations of the substances in the equilibrium will change. The equilibrium will not shift to either direction. Again, a catalyst does not impact the position of an equilibrium. We are basically done with this chapter. Here is a practice question for you. I will go over the question together with you. We will analyze the question together and make a decision on how to answer these kinds of questions. After that, you should pause the video, answer the question, and check the answer key after that. All right, let's go over the question. How would each of the following changes on the equilibrium shown below? There's an equilibrium shown below here. This is the equilibrium. And it looks like there are A, B, C, D. There are 4 changes applied to the equilibrium. How would each of them affect the amount of CH4? CH4 is right here in the right-hand side. How would each of the change affect the amount of CH4 when the new equilibrium is established? Will it be more or less than or the same as the amount of CH4 in the original equilibrium? All right, if you understand the question, good. If not, let's go over it again quickly. So there is a reaction system right now listed here. It is in the equilibrium. At this moment, at this equilibrium, the amount of CH4 is fixed. So there is, there is a certain amount of CH4 under this equilibrium in the system. Then one of these changes is applied, either A, B, or C, D. Once a change is applied to an equilibrium, the system is going to respond according to Le Chatelier's principle. Given some time, a new equilibrium is going to be established. It is asking you, under the new equilibrium, what do you know about the amount of CH4 compared with the original amount in the original equilibrium? Is it more than that, less than that, or the same as that? Well, how do we do this? First of all, we have done a few practices about how a change will shift an equilibrium. For example, if we say there is a change, and if that change shifted the reaction to the right, for example, if a change applied shifted the reaction to the right, then for the reaction to go to the right, some of the CH4 on the left will have to be consumed. As a result, the amount of CH4 under new equilibrium will be less than the amount in the old equilibrium. Does that make sense to you? For the same reason, if there is a change applied to the equilibrium, as a result, the equilibrium shifts to the left. While shifting it to the left will produce more CH4. Then the amount of CH4 under new equilibrium will be more than before. Now, if the change applied doesn't affect the position of an equilibrium, then the amount of CH4 will be the same as the amount in the original equilibrium. Does that make sense to you? Do I make that clear to you? All right, if you need more practice, you can modify this question a little bit. For example, this question is asking you for the amount changes on CH4. You can replace the CH4 for the same question. You can ask the amount of hydrogen or carbon disulfide, okay? How each of the following changes will affect the amount of those substances. All right, pause the video, answer the question, and come back to check the answer key. Here is the answer key. I hope you got them right. See you next time.